The paper that I want to present today was written together with Anna Abeljansky, who is a researcher at the Austrian National Bank, and Roman Stöllinger, who is now an assistant professor at the Technical University of Delft. And as Alexia already said, what we do in this paper is to combine two aspects with respect to workers and automation of the labor force, and that's the automatability risk of an occupation and the infection risk at work, to look at how they jointly affect employment, particularly during times of an increase in infections at work, and that was, in our case, this exogenous event of the COVID-19 pandemic that we used to identify the effect. I also should mention that this work is funded by the Austrian National Bank through a Jubiläumsfonds grant, for which I'm very grateful. Now, the basic idea behind this paper is that if we look at production processes, say 100 years ago, then what we get is a picture like this one, where we have, I think it's a factory of Ford, so the car company, where car parts are produced, and we see that this production process looks a lot like economists typically model production processes, where you have two types of production factors, here the human workers and physical capital in the form of this assembly line here, and the two are complementary to each other, so you need both of them in order to produce output. So without human workers you cannot produce output, and without the assembly line you can also not produce this output, so you really need both of these production factors to be able to produce. Now, if you Google modern car factory, the picture that you would see is typically looks like this one here, where you don't see any workers for many of the production steps. Instead, you see two types of physical capital. One is the traditional assembly line that we also had before, and the other is now what I call automation capital or robot capital, which basically assumes the role of labor that labor had in the past. And now, for the first time in history, actually it becomes possible to really fully and perfectly substitute for human workers with physical capital. And of course, this has a lot of implications, to which I will refer to later on. But this is a rather new phenomenon. This graph should convince you that this is a rather new phenomenon. This graph shows the number of worldwide operative industrial robots in industry that are used. And the first industrial robot was actually introduced in the 1960s and used by General Electric back then. And then we see that at least throughout the 1970s and 1980s, the number of industrial robots used in factories was still negligible. Only then there was growth, but it was still, so during the late 1980s, 1990s and beginning 2000s, it was still rather sluggish growth. And only since the global financial crisis, actually, 2008, 2009, there was really a takeoff. And we observed growth rates of the number of robots at the order of 15% per year worldwide. And that's, of course, as you all know, much faster than any population growth, any workforce growth, or any GDP per capita growth. So we really see an intensification going on in automation processes worldwide. And this is only one aspect of automation, industrial robots, but it's the one where we have the most data about it. But there are also others, so this slide should just remind you that industrial robots are very well suited in mass production, where you have kind of routine tasks that the robot assumes, but you can also automate customized production by the use of 3D printers or additive manufacturing, where particularly, say, things that have to be fit to every particular customer or patient in medicine that's used for prostheses and for hearing aids and so on, you can now automate production by the use of 3D printers. So in case of hearing aids, they are almost exclusively now produced by 3D printers. You have a scan of the ear and then you send it to the printer and the printer prints it, and it's really customized to every single patient. And that's kind of different from mass production, of course, where robots have been used also before already on a large scale. Then what I also put here is autonomous driving, just for the fact that this is an occupation with really a lot of employment, particularly in the United States. There are states where the truck drivers are the largest group of employees. And if this is automated, actually, at some point in the future, there will really be a huge structural change in the workforce because so many people are affected by that. And the fourth point is what we all witnessed over the last year, or a little bit more than 1 year, that there has been a lot of progress in machine learning and AI. We all have used ChatGPT, I think, and everybody was amazed how well this already works in writing reports, summarizing texts, translating texts, even coding, and so on. But there have been lots of breakthroughs already before in diagnosing diseases, which is actually a pattern recognition exercise where algorithms are very good at. So this IBM Watson was better than human doctors in diagnosing a lot of diseases that are rare, where doctors rarely see them, and even doing science. So in medical research, developing drugs, or in material science, where you have a lot of combinations of different possibilities, machine learning helps a lot. And even a theory was done by robots. So there is a paper published in Science in 2009 where they gave the algorithm just the data of a coupled pendulum without any prior knowledge about it. And out of this data, the algorithm developed the laws of motion from Newton. So this should show that even theorists are not immune to automation. So we should be very careful. But that's just kind of a brief overview. And now coming to what the talk is about mainly. So there is a lot of literature in the last couple of years in economics already on the consequences of automation. So of course it has effects, as you can imagine, on productivity, economic growth, unemployment, inequality, and so on. That has been analyzed quite a lot in the last couple of years. And a little bit less research has been carried out on the causes of automation, but a few stand out, of course, technological progress. So if robots become more efficient, then you could expect more automation. High wages, so if firms face higher wages, they have more incentives to invest in automation. If there is labor market tightness, labor market shortages, firms have an incentive to invest in automation. And particularly here, I think the fourth point is important. Also, demographic change has been identified as one of the main driving forces of automation, because if fertility rates fall and you don't have a lot of immigration, then the workforce does not grow that fast, may even shrink, and that of course also implies an incentive to automate. And this can be illustrated here by a world map that plots automation density in the sense of the number of industrial robots per manufacturing worker or per 1,000 manufacturing workers, depends on which one, all across the world. And what we see here is that countries that are darker have a higher robot density, and countries that have a lighter color here have a lower robot density. Unfortunately, there are many countries without data, so that's the white countries here, but actually it's quite synonymous with having almost very few robots or no robots at all, basically this no data category. So what we see here is that particularly the countries with low fertility rates, South Korea, Japan, Germany, Italy, they are at the forefront of automation technologies. So they are the top 5 countries actually, among the top 5 countries investing in robots and building up robot capital stock. And countries that are at a comparable level of development in terms of innovation, income, and so on, such as the US or particularly the UK, they have a lower automation density, which is explained in the literature due to the fact that they have more immigration or a higher fertility rate. Particularly the UK had a lot of immigration from Eastern Europe, therefore labor was cheap and the incentive to automate was not that high, and France had a higher fertility rate and so on and so forth. But now what we want to do in our paper is to analyze whether there is also a role in automation adoption to play for health, and particularly for the presence of transmissible diseases. So we've seen this during the COVID-19 pandemic, that it suddenly became a huge issue, of course, contagion at the workplace. And robots have the advantage in this context that they cannot be infected, at least by biological pathogens. They don't transmit diseases, they do not go on sick leave, and they also do not suffer from long-run productivity consequences, such as in case of COVID-19, for example. Of course, robots would not suffer from these long-run consequences. And from an intuitive point of view, we would expect that this could have an effect, right? When the COVID-19 pandemic hits, we may see certain changes in terms of automation in an economy. And that's what we want to analyze. So our research question is whether there is an indication that the pandemic combined with infection risk at the workplace matters for employment of different occupations that are susceptible to automation. And for that, we first provide a theoretical framework that models the decision of firms of whether to invest in automation or in a human workforce, and kind of model this choice and how this choice changes when the pandemic hits. And then we derive 3 testable hypotheses from this theoretical framework, and we test whether they receive support on Austrian employment data that we got from Statistics Austria before and after COVID-19, where we can differentiate between age, employment, so occupation, skill level, industry, region, and gender, basically. And we can test basically the 3 hypotheses that we have. And yeah, I mean, as a spoiler, we find support of these 3 hypotheses basically in the paper, where I would say that one is only the first one is only supported by kind of correlation type of evidence, but the second and the third, I think we could claim that there is really a causal identification as well. So how would we do this? And I will first present the theory, but I will just present the main intuition and will go through it from an intuitive point of view. And we have here that we kind of assume there is an economy, and in this economy a certain good is produced. This good is YT, and this good is consumed by all the individuals in the economy, right? And the firms produce the good by using physical capital. So these are the assembly lines with an output elasticity 1 minus alpha. So it's just a Cobb-Douglas type of production function. And then along these assembly lines, J different tasks have to be performed on the production step. So that resembles basically this picture here, right? So you have the J different tasks along the assembly line that have to be performed in order to produce output. Now, what we do differently to this picture is we allow that these tasks are either produced by robots or by humans, and it's a choice of the firm of which production factor it employs. So it has these J tasks with an output elasticity of alpha. Now, if a firm operates in a competitive environment, then the profit maximizing demand for such a task would be that the firm maximizes the profits, and the profit maximizing employment of one of these tasks, x t omega, can be determined as the marginal product of this particular task in production, because the marginal product means how much does production increase if I increase employment of this task a little bit. And if the price of the final good is normalized to 1, that's also the additional revenue that is generated. And for the profit maximizing firm, it would do this exactly if the additional revenue that is generated more than offsets the cost. And the cost would be the wage rate if the firm produces with human workers, or the cost of a robot if the firm produces with a robot, right? And so we can derive this inverse demand function for the different tasks as the derivative of the production function with respect to employment of one task. So we see that's the derivative of this function with respect to xt omega. So alpha comes down from the exponent. We have the exponent minus 1. The sum drops out because this particular task only appears once in the sum. And this is then the price that such a firm is willing to pay for a task, either if it buys the task on the market or if the task is bought in-house by the workers or by robots. So both is possible, and they are kind of isomorphic assumptions here. And now we have the task production. And this task production is so xt omega, that's another sector or in-firm kind of task suppliers that supply these different tasks, and they can do this by either employing humans, L would be human labor input, where the productivity of human workers is AT omega, and this productivity depends on the infection risk at the workplace. If infections are higher, then productivity would be lower due to absences, due to long COVID, due to firm closures, and so on. So infection risk would reduce human productivity. But the firms could also choose to produce with robots. This term here, P, stands for programmable labor, if you will, and robots also have a certain productivity at the particular task, omega, right? And this productivity of robots is not affected by the infection risk. And then we have an output elasticity of beta, so that's just, we have diminishing returns as you would basically have it. Now, the crucial point is that all these tasks that have to be performed on the assembly line, they differ in terms of the productivity of workers versus the productivity of robots. So there are some tasks that are very easy to automate, right? So for these tasks, the productivity of robots would be very high, particularly compared to humans. So firms would rather use robots whenever it's possible, right? And there are other tasks for which the opposite holds true. So, for example, there was this case of this speed factory in Nuremberg of Adidas. They wanted to have a perfectly automated production of sneakers there, and they managed to do this except for one production step. So everything could be done by 3D printers, automatic sewing machines, and robots and so on, except the step of putting the shoelaces in. So that was just not possible to automate it. So for this particular task, the robot would have a low productivity, and humans would have a high productivity. So you can imagine there is a sorting of tasks. The tasks that are very easy to automate would be more likely to produce, so the robots would be more likely to be used for them. The tasks that are difficult to automate, humans would use them, and somewhere in between maybe a task for which firms are indifferent. And that's basically what we compute here, where we write down the profit of a firm that supplies these tasks, or a firm, I should say, so a firm, if it's an outside firm, but it could be in-house task suppliers, so it could be the workers. And the profit would be the price that it can charge for a task multiplied by the amount of tasks that are produced, minus the costs of doing so, which is the wage rate multiplied by the number of workers if this task is performed by humans, or the cost of the robot multiplied by the number of robots if the task is performed by robots. And the cost of robots, that's gamma, that's how much physical capital I need to produce a robot. So that's the price of a robot, if you will, in terms of physical capital. And R is the interest rate, that's the cost of physical capital. So the product would be the cost of using one robot in production. And then one can maximize this this function with respect to the employment of workers and with respect to the employment of robots. And this is the point. You have a question? Yeah.
Is there any depreciation for robots?
Actually, we abstract from depreciation for the moment. It's kind of, if you assume the same rate of depreciation for robots and assembly lines, then nothing would change. They would just cancel out. Difficulties arise if you assume different depreciation rates. And here, it makes things actually quite a bit more complicated to compute without, I would argue, leading to much more additional insight, because then what you just have to carry over is always the difference in the depreciation rate between assembly lines and robots, and kind of the larger it is. So if robots depreciate very fast and assembly lines do not, then it would tilt the investment decision a little bit in favor of standard machines, but it does not change the results fundamentally, particularly not in this rather partial equilibrium setting where we assume the traditional physical capital as given. So we assume firm size as given and just analyze the incentives of such a firm with a given size to invest either in a robot in the production process for the tasks, or into humans. So for this paper it would not matter at all, and for other papers it's usually the case that it doesn't matter if the depreciation rates are the same. It matters if the depreciation rates differ, but then it just has the expected results that it tilts the investment decision in favor of the one with the lower depreciation rate. Yeah. Thanks a lot. Yes?
I probably had a similar question, but I'm not so familiar with the terms of economists. So just, I was also thinking, if you're taking into account the lifetime of the robot, which might be shorter and they could not be infected, but sick in a sense. But I think it's the same point, no? So that they have software problems or whatever.
Yes.
So this is the same point that you just discussed. Okay.
It's essentially, I think, the way you would model it, perhaps here by using the depreciation of robots. That would be one possibility. Sorry. And another possibility would be that you also write it into the productivity term. So that's something that we try to, as a follow-up project, analyze how cybersecurity risks actually affect the whole thing, because there you have networks of robots, and the larger the network grows, the more susceptible it is to, or the higher is the damage that you can have by, but that would then not be a biological pathogen, but a kind of cyber pathogen or whatever. So, and I think this is a very relevant question, but here we still abstract from it. Yeah. Thanks a lot. Any other questions at this point? Yes, yeah?
I was thinking, don't we need also a person who will push the button? And how do you implement this in your equations?
Because these are extra costs somehow.
A robot, in terms of that you still need one worker to kind of push the button or maintain the
decisions. let's
or make
say,
the decisions. Yeah.
about running the chain and everything.
Yeah. So here it is abstracted from this small cost in some sense. We have another paper where we go more into the details of that you need a certain type of worker to maintain the robots, basically. So there it's main. So we have then 3 types of labor. You have management. Management is not automated there, at least yet. But who knows? And then you have the engineers that design and maintain the robots, and then you have the workers who are on the assembly line, and they are kind of what we show and what we focus on. It's also similar to the paper that we have a little bit, where that the workers suffer from automation, but these groups that maintain the robots and management and so on, or the firm owners, so they gain from automation. So there are these differences, and these costs may matter, but here we abstract from these costs. So we assume basically that once you put this up, in terms of these costs, you push the button, basically that's in this cost, and then it runs until it breaks down. Yeah. So, thank you. Any other questions? Yeah, so, but if this is the case, then we would have the profit function here, and we can maximize profits either for firms that produce with robots or for firms that produce with labor. So we would take the profit function, the derivative with respect to the corresponding production input, and set it equal to 0, and we can then back out the profit maximizing input, labor input for the firms that produce with human labor, and robot input for the firms that produce with robots. And these two expressions are very intuitive, so you don't need to be concerned about how we derive it, but they are very intuitive. So what we see here is the exponent is negative because alpha and beta are smaller than 1. So if we have an increase in the wages, the demand for labor would go down. And that's intuitive because the costs for firms increase, so they would employ fewer workers, right? Then the second thing is, if capital increases, that would be the firm size effect. So we don't model capital endogenously, we just say, okay, the firm has a given size that is determined by the number of assembly lines it has. That's physical capital. If the firm is larger, so if K is larger, then the firm would ceteris paribus need more workers to staff the assembly lines. And a similar argument holds true with respect to robots. So the cost of robots would reduce the use of robots, and the size of the firm would increase the use of robots for the firms that produce with robots. And what's a little bit more involved is the interpretation of how productivity affects employment, because we have two opposing forces here. So if human productivity increases, you need fewer workers in the production process, but at the same time it becomes more profitable for firms to hire more workers because they are more productive, they can produce more, profits would go up. And this effect actually is stronger, which we can show by the exponent here, than this productivity effect. So when the productivity of a factor goes up, you would use more of this factor, which is the intensive margin of choice. And what we will see next is that there is also an extensive margin of choice, in the sense that if the productivity of a factor changes, then this affects the decision threshold for firms to invest in robots and in versus automation. So that's the next step. So here we have the intensive margin choice between workers and robots, and the extensive margin choice is basically we plug these expressions back into the profit function, so in this function here, and then we can calculate the profits for firms that produce only with workers. By setting this equal to 0, then we calculate the profits for firms that produce only with robots. So we plug the robot solution in here, from here, and set the workers equal to 0. And what we get are the two profit expressions. And then, as I said before, you can have a sorting of tasks in the ascending order of automatability, or descending order in this case of automatability, and you get that the tasks that are easy to automate are done by robots, the tasks that are difficult to automate are done by humans, and somewhere in between is the task for which the two profits would be the same. So the firm that the task producer that produces these tasks is indifferent of whether using a robot or employing humans. So it could do both, would lead to the same level of profit. And then, so we set these two expressions equal to each other, then a lot drops out, and we can then determine the threshold level of productivity at which firms switch their production choice, right? So what we have here is, on the left-hand side, we have the relative productivity between human workers and robots, and on the right, we have the relative cost, the wage rate divided by the cost of a robot. And the right-hand side is typically given in the economy, so you have a certain interest rate, you have a certain technological transfer rate with which you can produce robots, and the wage rate is also given. But the left-hand side changes over tasks. The left-hand side is this relative productivity. So, for example, for putting these shoelaces in, the left-hand side would be very high. So humans would be very productive. So then the left-hand side would be larger than this one. So this task would be performed by a human. And if there is another task, say, I don't know, simply, I don't know, throwing a hammer on something, where the robot can do this 24 hours a day, 7 days a week, without getting tired, that would then be a high productivity for robots. So ATP, omega would be high. And then this would be lower than this threshold, and the production step would be performed by robots. So graphically, you can illustrate this by this graph here. Say these are all the tasks ordered in the terms of relative automatability. So here are the tasks where robots are relatively more productive. Here the tasks where humans are relatively more productive. So these tasks would be produced by robots. These tasks would be produced by humans. And somewhere in between is this threshold for which the firm is indifferent. And now a pandemic occurs. So that's kind of the exogenous shock that happens. And when this pandemic occurs, this affects the productivity of humans, but does not affect the productivity of robots. So what we would have then is kind of the pandemic occurs, infection risk increases, relative productivity of robots increases, and therefore this would shift this threshold upwards. The share of automated tasks would increase, and the share of non-automated tasks would decrease, and on the margin, this is the extensive margin of the production choice, you would have more tasks that are performed by robots then. What's important here is that those tasks that are very difficult to automate would still not be produced by robots. And yeah, so this infection risk only changes the choice for those tasks that are comparatively easy to automate, right? So that's kind of what comes out of the model. And we can summarize everything that we have seen so far in terms of these three testable hypotheses. So we can say that the automation risk reduces employment. That's what we have seen in the intensive choice. So the higher the automation risk of a certain occupation is, the fewer workers would be employed in this occupation, so employment would be reduced, ceteris paribus. And then we have two hypotheses that are perhaps more interesting, because this one is already known from the literature also, but the two that are not tested so far is that the COVID-19 pandemic has a negative effect on employment on the margin, but only for those tasks that have a high automation risk. So what we should observe then is that employment of tasks or occupations then that produce these tasks intensively, that are easy to automate, they are affected by the pandemic, and tasks that are not easy to automate are not affected by the pandemic, basically, employment. And how we test this is we run a regression of this form here, where we have on the left-hand side the employment level in different occupations. So we have the data for basically all the differentiated occupations in the Austrian microcensus. We have the gender of the workers, we have the skill level of the workers, we have age, we have the industry, yes, and the region, and we have time t, where we have years before and after the COVID-19 pandemic hit. We control for all of these aspects and fixed effects, occupation fixed effects, industry fixed effects, and region fixed effects for education and for gender. But what we are interested in are these four terms here with the four parameters, beta 1, beta 2, beta 3, and beta 4. But the first one is the viral transmission risk in the given occupation omega. So that's really how much are you at risk to get infected at the workplace. Then beta 2 is a COVID-19 dummy, so it's only one in the years where COVID-19 is present in the data, and it's 0 before 2020 actually. And then we have the combination of these two, which we are actually interested in, namely the interaction term between the viral transmission risk and the COVID-19 pandemic, because what we argue is that before the COVID-19 pandemic hits, the viral transmission risk at work was actually not really anything that anybody cared about, right? And only after the pandemic hit, this was kind of may have affected the choice. And RTI is the routine task intensity of an occupation, so that measures how easy it is to automate the particular occupation in the data. So now our hypothesis 1, 2, 3 imply the following. So hypothesis 1, that there is the automation risk reduces employment, would mean that this coefficient beta 3 is smaller than 0, so it's negative. And hypothesis 2 and 3 mean that beta 4 is negative, but it's only negative for automatable jobs, and it's indistinguishable from 0 or approximately equal to 0 for those jobs that are non-automated, right? So that's the 3 hypotheses. And now the data sources that we use, that's we have data over the time period 2015 to 2021 from the Austrian microcensus. So Statistik Austria basically sold us the data. We have data on employment, hours worked, and work volume as well. So that's then, we have 2 different measures for employment. We have age, gender, education, industry, region, and occupation. And that's everything from Statistics Austria. And then we have 2 variables that we have to construct ourselves. That's the viral transmission risk, where fortunately this is estimated for the United States by a paper by Chernoff and Worman that came out in 2023. We had access to a working paper version of that already. And we used the results from their estimations and kind of used a crosswalk to the Austrian labor market and the Austrian occupational ISCAT 3 level, I think it was, to kind of construct this viral transmission risk index for Austrian occupations. And then we had also data on the routine task intensity, also for the United States, by Auto and co-authors. So they did this in 2003. It's a standard measure used for this routine task intensity that is usually used in the literature to proxy automation. And we again translate this to the Austrian labor market. And what we then get is the following set of results. So these are the baseline results. We have robustness checks and sensitivity checks in the paper, but these are, I would argue, the central results. We have here on the first block where we use employment as a dependent variable, and the second block uses work volume as a dependent variable. I will say a little bit more later why there is a difference. And we distinguish between automatable occupations and non-automatable occupations, basically according to a certain threshold in the intensity, routine task intensity, and what we now would observe, would kind of observe, if our hypotheses are true, is that the routine task index would have a negative coefficient size if hypothesis 1 was correct, right? And we see that this is the case, of course, for automatable occupations, but not for non-automatable occupations. And the interaction term between the viral transmission risk and COVID-19 would also be negative. That's also what we see here. And the third hypothesis says, okay, it's only negative for the non-automatable occupations. For the automatable occupations, it's indistinguishable from 0 for the non-automatable occupations. That's hypothesis 3. And this is exactly what we see in these results, right? So this beta 3 coefficient actually is negative, and significantly so. The interaction term is negative, and the interaction term is basically 0 in the non-automatable occupations. And in all of these regressions, we use the control variables, industry, occupation, and region fixed effects, and so on. So these results, I would claim, at least are not against our hypothesis. I would say this first hypothesis, that's more a correlation type of evidence that we have, but with respect to the viral transmission risk, I think you can claim that this is causal evidence because it was an exogenous shock that hit the economy, and you control for the viral transmission risk here anyway.
Klaus, if I read it properly, once you control for COVID-19, viral transmission intensity has a positive impact on employment.
Exactly, yeah.
How do you interpret that?
That was exactly the thing that when we saw it first, we were puzzled, but in the end it's a very straightforward explanation. It's that just the jobs where viral transmission is higher, they gained importance from 2015 to 2021, basically because there was still this transition to the service sector. and services being more personal services and so on. So once you control for kind of the viral transmission risk intersected with COVID-19, you would pick up the structural change by the estimate of this parameter. So you see that over time, the jobs kind of grew faster in services than in manufacturing. And particularly in services such as old age care and stuff like that, where the viral transmission risk is higher, and that's picked up by this estimate. Yeah, thank you. Yeah, and then another thing that we thought about is that I mean, if this is kind of the story, this infection risk, then we should actually observe stronger effects on the work volume than on employment itself, because we had the furlough schemes in Austria, right? So we had this Kurzarbeit, where basically the government subsidized workers or firms actually, so that they did not kick the workers out, but just send them home with, I think, 80% of the pay, but 0 hours. And these people would show up not in the employment statistics, because they still count as employed, but in the work volume statistics, because their work volume goes down, right? So if our story kind of should be credible, then we should actually see stronger effects for work volume than for employment itself. And if we do this, then this is exactly what we observe here. So this interaction term from the viral transmission risk and the COVID-19 dummy variable, that doubles in size, absolutely. So the effect would become twice as large in when we look at work volume than employment. So that would hint towards the thing that these Kurzarbeit schemes were as kind of effective in containing unemployment, but at the same time you see this, then the results are stronger here. Sorry. Yeah.
Can you define work volume?
That's hours worked, basically. So yeah. And hours worked, so if there is a person who is just sent home, but she does not count as unemployed, but the work volume would be 0. So yeah, and therefore you would expect this difference. And that's again what we see. So we hope that this provides some additional credibility for the results, and in addition it shows that if the results are kind of like this, that it actually shows that the Kurzarbeit schemes were effective in preventing unemployment increases, right? And yeah, so these are the main results, and just to illustrate kind of this, so I find this illustration quite intuitive, so therefore I put it here. Actually, it's just descriptive evidence, but I presented it afterwards because I think it's a nice illustration, actually. And I was kind of really surprised by the strength of the effect when I saw it first. So what we have here is, we have employment from 2015 to 2021, and we just group the total employment into 4 different groups. Those types of employment that have a high viral transmission risk, so a high infection risk at the workplace, and a high risk of automation, that's the solid line here. Then the group that has a low infection risk at the workplace and the low automation risk, that's the dashed line here. And then 2 groups in between that have either a high automation risk but a low infection risk, or a low automation risk and a high infection risk. But for the sake of the illustration here, let's just abstract for the moment from these 2. But what we see is that essentially for those groups that have a low automation risk and a low viral transmission risk, employment just increases throughout the whole sample. And there is nothing whatsoever when COVID-19 hit. So there is no change in trend, nothing actually, according to, eyeballing. But for the group that has a high automation risk and a high viral transmission risk, we see there is really a sharp change in this upward trend in employment when COVID-19 hits and afterwards it goes down, and leaving all the gains actually that it had from 2015 to 2019, which were actually even higher than the gains made in employment for the low routine task intensity and low viral transmission risk. So that's kind of an illustration of the results, but the evidence, so this would be just descriptive evidence, and I would say the more credible, the test of the hypothesis is indeed visible in these results. And so I think I can conclude here that we find evidence in favor of the hypothesis that automatability affects employment in Austria, but that's already what we know from the literature. But what is new is that the viral transmission risk affects employment during the pandemic, but only for occupations that are automatable and not for occupations that are non-automatable, and the effects are stronger for work volume as compared to just employment as such, which gives an indication that these furlough schemes have had the intended effects, and it gives some further credibility to the results. So usually I end with some policy recommendations, but I think in this case there are not really policy implications, except if you want to contain unemployment increases, then these furlough schemes kind of work. But apart from that, I think it's just the results that we tested that are the conclusions here. And once again, I thank you for your attention, and I hope that it was interesting to you, and I'm happy for all the comments and discussion points and so on that I get. So thanks a lot.